If Fabio runs over, like the other speakers, then he's not going to get any time for questions. So he knows the penalty for being late. And then people will sit next to you for a meal to ask their questions, which is...
Let me see if we can get the signal here. Oh, there we go.
Impatient. Okay, next talk is Fabio Capitanio, complex mantle flow around heterogeneous subducting oceanic plates.
Okay, thank you, Dave. Thank you.
Okay.
Yeah, the time maybe.
So
okay.
You have 3 minutes.
Yeah, so I started, I thought I might start with a beautiful picture full of colors to recap a little bit what we've seen so far in the previous talk, and also what we're going to see in the remainder of the talk, of the meeting, is that essentially it's important to understand properly the evolution of our planet, like we've seen before. It's important to understand the processes that are deep in the Earth mantle. However, the mantle remains concealed. There's no direct problem of the mantle. So the only information we have is data, and these data are mostly coming from tomography, like this picture you see in colors. Let's have a look. Oops. Maybe there's a problem with the timing out. We just started. Okay, so I'll probably swipe the mouse quickly while I'm talking. But so tomography is these images that you see here. So it's the recording of the seismic signal on the top that reconstruct the structure in the mantle, but also some other information that we recover from the motion of the plates on the surface, and eventually the stresses around subduction zones or on the surface in general. So usually, to have a better understanding of this process over geological time, we rely on modeling of subduction, for instance, which is the most important process that happens in the upper mantle. So I show you my model, but this is just representative of many models that have been published so far, and you've also seen some models before. So allow me to show you the characteristic of flow in subduction on my own model. So you have a three-dimensional model here. Some details will follow later on. You have the subduction here, so you start with a perturbation, the subduction evolves, the slab hits the 660, and you have a subduction interact with an upper plate. You only see the trace here. And the negative buoyancy on of the slab in the upper mantle rearranges the flow in the way that you see here. So it's a cross-section where the yellow line is. And you see essentially the slab is going down, sinking in somewhere in the center, and arranging the flow around. So you have a colloidal flow below and above that essentially accompany the motions. So you have essentially circulation of flow down here. There is no lateral advection, so no lateral flow. It's almost zero. So this is essentially a 2D picture coming out of a 3D model. And you can see also that if you take a cross-section somewhere here, this being the trace of the slab, you can see again that the flow goes somewhere away from the slab, or in any case in a direction that is usually called trench perpendicular, and it's only toroidal, so it goes around the slab at the edge, like for instance what you've seen before in the model that Margaret showed. This is really a compelling model. As explained a lot of observables. First, it explains the motions of the plate on a global scale, so it's relevant for the global plate motion, but also explains the arrangement of the flow as revealed by images of seismic wave splitting, here radial and azimuthal on both, and essentially you can see that the direction of the flow is aligned with the motion of the plate that essentially move from the ridges to the trench, like we all know. But it's like Margaret told us before, it's when we get closer to the trenches that the things are a bit more complicated. I'm not going to talk today about what happened in the mantle wedge. Margaret did an excellent job about that. But I'm going to talk to you about the fact that the SKS splitting, so the splitting in general seismic wave, for the sub-slab, so you can see the red arrows here, so below the slab, they always align everywhere in the world except few cases. They always align somewhere like parallel, trench parallel, with some complication here, but everywhere a little bit trench parallel. In the mantle wedge we might have a lot of complication, but below the slab it's a rather homogeneous mantle down there, so we don't expect anything complicated, if not something that is related to the flow. And this is what prompted Ray, Russ, and Paul Silver long ago to propose that the mantle flow underneath the end, this is trench parallel. That was really coming as a shock because the models never show that, and yet the models, they don't show that, so they've prompted some more research in the field of analysis of the seismic data. We will see something about it later on. So the question that we ask with my friend Manuel is there any complication we are overlooking around subduction zone? This is a beautiful picture from the group of Dietmar Müller in Sydney. It's the age of the oceanic lithosphere. So we can see that essentially it's never constant. So is this true that a slab, a uniform slab is subducting down there? Not apparently, because the age of the oceanic lithosphere, we all know it's a textbook nowadays, can be translated into the thickness of the subducting plate. So that's what and this varies along all the trenches all over the world. So this is a little bit the idea that is underlying this work that I'm presenting today, in which if you just take, for a specific temperature, you take the thickness of the oceanic plate in time, you can translate this difference in ages from 10 onward to up to 80 million years. You can translate the difference in ages in different in thickness. And we've been trying a little bit everything in the models. We've been trying to change the thickness along the y direction, so along the trench. We've been trying to change in the density as well, and we've tried some other configuration. There are perturbation of a steady state and some other. Some details of the numerical model here. I'm not going to go into details. It's been already presented. It's incompressible, it's Bose-Nesque, that's a Stokes. And we have a lithosphere that is Newtonian, non-Newtonian mantle, because this most likely is going to represent the rheology of the Earth mantle. Some plastic behavior here that allows the decoupling of the upper plate, the subducting plate. But most importantly, we have put a homogeneously thin plate somewhere, and then at the center we have changed the thickness, so that eventually we end up with some variation of thickness or buoyancy, integrated buoyancy along the trench. What happens is this is a picture like the one before, so after subduction starts, we have the development of a slab, arrangement of flow. Of course, needless to say, it's more negatively buoyant in the center. It's going to be faster in the center at depth. If we have a look at the cross-section here, where the yellow line is, so it's 1,000 kilometers from the center, let me tell you that this model is 3,000 kilometers wide, and it's symmetric, so it's representative of 6,000 kilometers wide subduction. So essentially the flow here is the same we've seen before. So the slab goes down, rearranges the flow, convection cell here, another convection cell in the front, in the mantle wedge. But if we have a look in this cross-section, the velocity that is trench parallel, so it's perpendicular to the plane of the screen, we see that this field is non-zero. There are some places where it is large. Just to wrap up everything, the two models are compared here, and where there is a triangle here and crossing this star there, I made a vertical profile that shows you that in these two models, the red curves, they are essentially the same. This is the flow, the counterflow that is associated with the motion of the plate, subduction motion on the surface. If you have a look in the blue line, along this vertical here, the flow that is coming out of this plane of the screen, we see that it is negligible in the dashed line, up model above, and it's not negligible in the other one. It's still small, it's not large, it's something like a third or even less, but still it's characterized the whole mantle, so from the whole flow. How can you explain that? Well, it's easier to have a look at the model itself. So this is how it goes. So while the model is essentially this poloidal circulation, so this is a view from the back of a rendering of the slab in gray, and color is the velocity in y, and these lines, the straight lines, are the path of some particles that are immersed in this flow. So what happens? It happens that still has this 2D effect. So the poloidal flow is accompanying the motion towards the trench of the slab. But when it gets closer to this step in thickness that you see here, and buoyancy you see here, essentially gets dragged along, and at a certain moment gets entrained and flows for very large distances, these being 2,000 kilometers, eventually reaching the toroidal flow on the side. This is I would call it the experimental evidence, but we've been investigating in what might be the cause, the mechanism, just to make it simple to all of us. So in principle, when you see the cross-section taken here, where the star is, what you have in this model, you have a velocity that is trench perpendicular and becomes toroidal here. In this little point here, by the velocity Vy, so along the trench are really small, the velocity perpendicular to the trench in the poloidal in the plane perpendicular to the trench are 0. So here is a place where the flow is completely dominated by a trench parallel flow. It's not trench parallel elsewhere, it's at an angle, as you've seen, but somewhere there is a slight, in this thin layer here, there is a dominance of a trench parallel flow. But what is this causing this? Why the pressure gradient here is 0, so the pressure is constant below, it was expected by simple fluid dynamics law. What we have here, what we have here is that a pressure gradient develops following the buoyancy structure of the slab. This is, let me see, is frozen. Just a second, seems like it's frozen. Excellent. Panic. I'm sorry about it. Oh, there you go. Let me see if we get the signal on the screen. Okay. So to understand what is the underlying mechanism of this effect we found from the model, is essentially, we explain this in this way. We know that there is a pressure in the mantle, it's, oh my god. It might be, it will be, because we all have in the same problems anyway. Yeah, cross your fingers. So we know that the pressure in the mantle is the result of the shear-driven flow. So you have a viscous mantle that is essentially shear, and this motion on the top, imposed on the top by the subducting plate, they create a pressure. So therefore, if you have a constant slab velocity, like you see in this model, along the trench, you might expect also that you have a pressure due to the shear-driven flow. Oh my God. That is constant, so that explains what we've seen before in the model. Instead, if the velocity of the plate that shears the mantle varies laterally, what you have is that you have essentially a pressure that varies following the velocity, and therefore might start a pressure-driven flow laterally because you have gradient in the pressure. So we can proceed to the next slide. Very luck. Okay, there you go. So taking a simple, some simplification, like the slab dip is constant and viscosity also, we can essentially start from the definition of the shear-driven flow, derive the derivative of this, plug it in the pressure-driven flow, and find somehow a rule of thumb, a scaling law for the lateral velocities. And if you vary, like we've been doing in this model that I show you, we've been varying the size, the width of this thick portion in the center, and essentially you see that you can create some pressure gradients, some velocity gradients in the subduction, as you can see here, that varies. This is the velocity of the plate in the mantle, and eventually you plot them all together and you see that with the increase in size of this perturbation here, you have increase in lateral velocities, and in dashed line is that you can recover with this very simplified rule of thumb, which somehow tell us that the physical principle behind this is kind of appropriate to describe what's going on there. But there are a couple of things that I want to warn you about before we draw some conclusions. First is essentially, you see here in colors that there is a large gradient of velocity of the slab in the mantle, but you don't really see such a thing on the surface. This is because on the surface the plates are much more rigid than the slab sinking in the mantle, where the pull is applied on different planes, perpendicular to the plate or along the plate. And in principle you see that the velocity of the slab at depth, they might vary largely, but still, if you take the velocity of the surface, they are much smaller, and especially the gradient, essentially they are almost negligible. And in principle, this constrains one of the major observations that we have, that is the velocity from the surface. So there is from the surface we don't observe any gradients, so we cannot really infer anything on the structure of the mantle down there to at least this detail. We can have a first order, but not the second order gradients. The other caveat is essentially that when the perturbation is really small, you can see here that the thickness is the same, but only the size, the width of this block, this thicker portion is larger. But when they're really small, the slab pool gradients that they confer while subducting are essentially resisted by the internal stresses in the slab. This doesn't happen when this is larger. So you can see that when it becomes larger, the pressure gradients, they increase. And this is essentially because plates, they have a mechanical stiffness, which scales with the viscosities and with the cubic root of the viscosity contrast and the thickness, just another rule of thumb. And in principle tell us that the size matters. So everything that is perturbing the buoyancy field of a slab that is smaller than what the plate can accommodate with internal deformation is likely not going to affect much, nor the plate motion, not even the flow. And so I can draw some conclusion here that, again, comparing the two, I'm not going to insist on this model. There's a lot of things in this model were not really appropriately describing what's going on there, but maybe we have some modeling now, we have a starting point to reconsider a little bit our understanding of the processes down there. This is a model that is similar to the one in the Andes, and I've been doing some work before, published last year, in which I can also show you that the same model, this is essentially the same, but there is a symmetry plane here, so now this is a 6,000 model, so it's essentially double. And you can see that if you have just a slab with no perturbation in their buoyancy, the stress on the surface is essentially constant along the trench. So you can't really explain the thickening of the Andes. By thickening, I mean just the increasing of the thickness of the crust by uniform thickening. Instead, if you apply the same small or second order slab pool buoyancy gradients, you will end up with something that really looks like the thickening in the Andes. So it's an additional constraint to this type of model. So more in general, this is the second time of conclusion, plate surface velocity are not really sensitive to the complexity of the mantle down there. So we might be really overlooking, understanding the first order, but we might really overlooking the flow around the slabs by a great deal, I would say. And more in general, this is a message to the audience. With the slab pool models that I put in my model, they're essentially driven from the idea of the age changing along the trenches. But similar slab pool gradients, they will be found everywhere you have the depth of subduction that is changing, some tear in the slabs, like Pizzogoni-Maniana, windows in the slabs creating small-scale slab pool gradients, but also the subduction of continental block. And this might be really relevant in the organization of flow around subduction zones, but also in the stresses that are propagated to trenches. Thank you very much.
Hey. Any questions?
Okay.
Perfect.
Excellent. What did I get? A beer?